discrepancies in our blast curves. Getting the answers was our priority objective on Tumbler. Several things could be happening. For one, the shock-reflecting characteristics of the target itself might be a factor. For another, the thermal radiation might cause the dust on the ground to stir up to such an extent that it cushions the shock wave. It might heat up the ground and the air layer close to the ground to such an extent that it would alter or soften the full effect of the blast or the development of the total potential force of the reflected pressure wave. On the other hand, perhaps there is a completely unknown reason why our estimates of the optimum height of burst for an atomic bomb were wrong. So nuclear weapons were used for the purpose of establishing new blast curves at the Nevada Proving Ground in the spring of 1952. The first weapon will be detonated over Frenchman Flat, site of Operation Ranger in 1951. This is a dry lake bed with moderately stable soil and generally high thermal reflecting characteristics. The blast measurement line stretches 4,000 feet west from ground zero. 50-foot poles were placed every 250 feet along the blast line, with instrumentation running from ground level to the very top, changing the lake bed from its normally flat, deserted appearance to that of an outdoor scientific laboratory, complete with intricate instrumentation of all sizes and purpose. All of this will help determine the blast characteristics produced by a nuclear weapon over this type of target, and to extensively study phenomena occurring in the air layer close to the ground. To aid the many projects in making a more complete evaluation of their results, the Air Weather Service is installing special instruments to record wind direction, speed, air temperature, and relative humidity. This data will help by recording the exact meteorological situation around the test setups at shot time. Another instrument, known as a blast switch, will record the time of arrival of the shock front at ground level, 10 feet and 50 feet. These are installed at stations along the blast line to give us additional information on blast and its behavior as a function of time and distance from zero. The next set of instruments, Wianco gauges, located at 3 elevations on the pole, will measure variations in pressure with time and distance. Gauges on the pole are parallel to the blast line, and at ground level are flush with the earth. The gauge itself incorporates a pressure-sensitive recording element placed behind the hole in a 17-inch baffle. We're trying every angle and every gadget we can to find out what really does happen when an atomic bomb kicks out fiercely at the world around it. To get a picture of blast pressure driving into the ground, we're installing self-recording accelerometers 5 feet below the surface. At this shallow level, we hope to obtain data on movement of the shock wave, both vertical and horizontal through the medium of Earth. Other accelerometers placed to a depth of 50 feet will record the deeper responses. To get still another cross-check on the shock front or blast wave, as its arrival time is clocked by succeeding stations along the blast line, we're utilizing another type of blast measurement instrument called a Bendix gauge, installed at ground level at each of the stations. At 10 feet and ground level, we're installing dust collectors to see, first of all, if the thermal phase does kick up dust, and if so, to determine the size and density of the material that could possibly be a factor in reducing the power of the shock wave, besides absorbing and retaining some of the heat. By establishing air temperature at ground level, at 10 feet and at 50 feet before the burst, during the period of thermal radiation, and during and after the shock wave, we hope to get one check on the effect of this hot air layer on the shock wave. We're using a self-recording temperature measurement device called a thermocouple, which contains a very delicate temperature-sensitive element capable of recording temperatures ranging from normal temperature on the Nevada desert up to 1,000 degrees centigrade and back again to normal in a few fleeting seconds. At some of the closest stations, we're installing other types of air temperature gauges, 2 and 4 feet above the desert floor, to further our studies on air temperature versus time in proximity to 0 point. We're installing another gadget, a sound velocity recorder, to give us still another cross-check measurement of the temperature of the air above the ground at the time of the burst, during the period of thermal radiation, and up to the time of arrival of the blast wave. This is done by measuring changes in the velocity of sound produced and received by the instrument. We hope this will prove to be still another way to determine the interference of the hot air layer close to the ground with the subsequent blast wave. By sundown the day before the shot, we had our blast line poles fully decorated like a row of weird Christmas trees. The working scaffolds had been pulled down, the cable trenches filled, and the area leveled. Our job is over for the present. All we can do now is wait. What has been feverish activity during past days and weeks suddenly becomes quiet, studied, in a way desolate. This is the last check, the final inspection by Los Alamos and military test directors as they survey the blast line with its complicated array of instrumentation above and below the ground. All is secure. Frenchman Flat stands alone and ready for the first shot of this operation. Shot day, 0 hour minus 10 seconds. The drop plane has released the first weapon of the operation. And as the bomb falls, smoke rockets are fired to form a grid. High-speed cameras record their responses as a measurement of blast pressures above the ground. This bomb is not a test of a new idea, but a weapon with a 1 kiloton yield detonated at an altitude of 800 feet to closely correlate the effects with the low-yield bomb of Buster Baker. Once the dust is settled and the safest routes for re-entry are chosen for us by the RadSafe people, we quickly move back to the blast line stations to recover our instruments and their very hard-to-come-by data as soon as we can. Although radiation levels are high and working time is short, it's perfectly okay for us to go in and pick up our priority data. We're all understandably anxious to get the answers, although this may take weeks or months of study and evaluation before the final determinations are made. With the first shot of the tumbler phase completed, we're taking the rest of the weapons north, some 10 miles across a ridge of mountains into the next valley, Yucca Flat, site of the Buster operation, to try different heights of bursts over a completely different type of target. Stretching to the south, 12,000 feet from ground zero, are the various military effects measurement lines. The blast line here is basically a duplication of the Frenchman Flat blast line. The target is a bullseye 500 feet across. By comparison with the lake bed in Frenchman Flat, the surface in this area is rough and dusty. By comparison with data we got at Frenchman Flat, we hope our instruments here will tell us if the thermal absorption characteristics of a target affect the shock wave. Here we will also get a valuable check on the effect of the height of burst, on the development and effectiveness of the shock wave and Mach Y stem. Tumbler, Shot 2, 15 April 1952. The weapon for Tumbler, shot number 2, is the same size as the one detonated over Frenchman Flat. Yield, 1 kiloton. Height of burst, 1,100 feet. This gave us a chance to detonate the same weapon over both a reflecting and non-reflecting target. 22 April 1952. Tumbler, shot 3. Weapon yield, 30 kilotons. Height of burst, 3,500 feet. The same scaled height as shot number 2. These two tests should together provide an excellent check on the normal blast scaling laws. help the defense establishment produce their new height of burst curves, the Air Force dropped the weapon in a standard ballistics case. Tumbler, shot 4, H minus 1 minute. Yield, 20 kilotons. Height of burst, 1,050 feet. We have had the opportunity to measure and study the characteristics of blast, the basic destructive force released by an atomic bomb. To study it in the course of 4 detonations over 2 types of targets, 3 different heights of bursts, and 3 different yields. The Tumbler operation provided good experimental data on which we can base new height of burst curves for operational use. These curves falling between the old theoretical curves and the data obtained during Buster, providing for the first time experimental proof of the advantage of detonating an atomic bomb high in the air when weak targets such as aircraft are involved. We also found that the normal cube root blast scaling laws developed from high explosive tests apply to the blast pressures from atomic weapons. A new phenomena which may account for the low pressures measured on previous tests was observed for the first time on the 4th shot of Tumbler, a so-called precursor pressure wave moving out from ground zero in advance of the incident shock wave from the bomb. This precursor wave may be caused by the intense thermal radiation released at detonation. We'll have to study, analyze, and cross-check, and then return to our outdoor laboratory again to proof-test our findings. But blast phenomena wasn't the only thing studied on Tumbler. Let's go back and take a look at some of the others. Before Tumbler, there was little information about the effects of blast on aircraft dispersed in the vicinity of the burst. We didn't know for sure how much blast pressure an aircraft could withstand and still take off on a mission. So we moved a variety of aircraft types into stations at various distances from ground zero. The aircraft themselves were positioned in a variety of orientations to the burst. Some faced directly into it, some directly away, some at oblique angles, some at right angles. Will orientation be a factor? If so, how much? Since a fighter is built to withstand greater load factors than a bomber, will the fighter sustain less damage? Will jet planes, which are built to withstand the great pressures of high speeds, sustain less damage than conventional aircraft? We're primarily attempting to define the damage area limits under the different conditions of detonation. So if a plane was not damaged on one shot, we moved it closer for the next shot in an effort to find the breaking point. Some aircraft themselves are instrumented to record the strains and pressures inflicted upon them. We're backing up the instrumentation in the planes with thermal measurement instruments near them on the ground. We have positioned some of the planes behind shields and revetments to help us analyze the value of passive defense for enemy aircraft and for our own planes. We're going to get a lot of valuable information, too, on the effort required to return aircraft to an operational status after exposure to a burst.